Hi guys, so that might be the last video of the playlist, and then I will try to start a new playlist covering waves and sound waves and maybe Doppler effect. So that's gonna come next because those questions very often you find them in the MCAT exams, for example. So anyway, last time I forgot to show you this video. And you see the first mode, the natural mode of a tuning fork, and that will be the mode that holds on, right? That will produce that pure tone. Okay. So if you look at the wave form produced by the tuning fork, it's going to be a perfect sine wave with the frequency here, with only one frequency. The frequency usually is given here, and the number of vibrations that you get per second will be the frequency. Okay, so number of cycles per second. That comes from the channel I was referencing to last time. Also, another very good website is this one. It's called Hyperphysics. So last time we talked about the tuning fork. Again, the tuning fork. This is the first mode. So that's the one that holds on. And here you have the equation to find this first mode. And you see, it depends on the speed of the wave here. And the speed of the wave depends on the restoring force and inertia. Okay, so of course, if you have more, if the density is larger, so you have more inertia, so the speed will be smaller. And the Young's modulus has to do with the restoring force. So if you have a large Young's modulus, that means you will have the restoring force will be more efficient. It's like if you have a stiff spring, the restoring force will be larger compared to a flexible spring. Okay. And then it depends also on the physical properties of the object that is in vibration. So it depends on the thickness here, from here to there, and it depends on the length. Okay. So it's interesting website here. So here are the examples. If I look at the drum, you see that the fundamental again is a function of the speed here of the wave, and the speed of the wave depends on the restoring force and inertia. Okay, so it depends on the mass per unit area. The tension here is the restoring force, and it also depends on the physical properties, so the size of your instrument. So there is all physics, trying to find experimentally, in many cases, the frequencies, the resonance frequencies, all the modes. So another website that if you're interested in the physics of music and the physics of sound, this is a very nice one. And he developed a lot of simulation using MATLAB. And for example, very cool simulation, vibration of a baseball bat, right? So you can use MATLAB, and you can find all the modes. So that will be a baseball bat, and you can find the frequencies, the natural frequencies, and you have also like very interesting stuff like the vibration, and you have to do experiment to find those modes, right? So the vibration of a beer bottle. Okay, so you see all the modes. So I thought that was really cool, and you can do all kind of analysis. You can analyze, and you can visualize all the natural frequencies that the bottle likes to vibrate with. So another recommendation here. So let's finish the problems here. Let's just review. It's a nice and easy, only algebra based, but it's a still nice review. So let's try to do this one. you can pause the video and try to do them. Number one, it's here. So let's see. What do they ask? So it's tightened. It's a rope and it's tightened at both sides. So here that will be the length. And here you have the mass. Okay. And here you have the tension. Okay. It's fixed and held taut, and the end of the rope is moved up and down and the frequency 2.5. Okay, so it's tightened at both sides and you have the frequency here. So that will be very much like the simulation I showed you last time. Okay. What is the mass per unit length? Okay, so that's easy. So the mass per unit length. So if it's linear, we call the density rho, and that's going to be, no, actually, I have called it rho, but it should be called, in the equation I show you, I think it's called mu. I'm going to call it mu. So it's going to be the mass, so 2.4 divided by 8. Okay, so this is kilogram, that's meter, so it's good. And it's going to be 2.4 divided by 8 is going to be 0.4 kilogram per meters. Just kidding, it's 0.3 kilograms per meters. Okay, so that's for A. B, what's going to be the speed? So the speed is, so it's speed, so it's a scalar. It's the square root of the tension, which is like a restoring force that wants to bring back each oscillator to its equilibrium position divided by mu. So it's going to be the square root of, so that's going to be 30 divided by 0.3. So it's going to be 10 divided by 0.1. So it's going to be square root of 100, which is 10 meter per second. C, what is the wavelength? Okay, so we want to find the wavelength. So the wavelength, you know that the wavelength of this wave that you can produce on that rope. So we can use the equation. The speed is the wavelength times the frequency. So the wavelength of this wave equals to the speed. So it depends on the speed. So 10. And then you divide by the frequency, right? So it's going to be 10 divided by the frequency is 2.5. So it's going to be 4 meters. Okay, D. So how many cycles of these waves will fit on the rope? So it's 8 meters long, right? So from here to there, it's 8 meters. And the size of the wave, so the size of one cycle is 4 meters. So how many of these can fit into this rope? So that's going to be 1, and then it's going to be 2. So it's going to be 2 cycles, 2 of them. two, uh, 2 cycles, 2 feet. Okay, so that's going to be 8 meters. So 1, 2, 3, 4. So that means the fourth harmonics. So that will be the fourth harmonics or the third over 2. Okay. So E. So if I want to find the fundamental, then you divide by 4, right? You do 2.5 divided by 4. And then E. How long does it take the leading edge of the wave to reach the other end of the rope and start coming back? So it means how long does it take to go from here to there? Okay. So the speed is distance divided by time. That's all there is, right? So to reach the other end and start coming back. So it didn't come back yet. So it didn't go back and forth, just one way. So the speed is 10. So 10 equals 8 divided by t. So t equals 8 divided by 10, which is 0.8 seconds. Okay. So that will be 1, 2, 3, 4. That will be the fourth harmonics, the third overtone. So if you want to find the fundamental f sub 0, f sub 1, it will be 2.5 divided by 4, right? Okay, so let's do next one. So let's see next one. So the guitar. Let's do the guitar. Still the same kind of problem here. So a guitar, so you have the length and you have the mass. So that's the total length. Okay, so that's the total length of the guitar. Once on the guitar, however, there is a distance of 64 centimeters between its fixed ends. So the standing wave will only be on that part of the string, right? So that will be the L that you're going to use in your equation. So that's going to be 64 meters. That will be the total length of the string having a mass of 0.04 kilograms. So that will be the tension T. So A, the mass per unit length. So the mass is 0.04. And here I have to put the total length. So it's going to be 1.25. So what do I get? It's going to be 0.032 kilogram per meters. So you should check, but I didn't double check here. So it's going to be 0.04 divided by 1.25, 0.032. Again, you should pause the video, try to do them. B. So what do they want? They want the speed. The speed of the wave on the string. So it's going to be the square root of the restoring force or the tension divided by your inertia, which is a density here. So 0.032. And that's going to be 150 meters per second. So C, the wavelength. So the first one. So the first one will be 2 times L. Sorry, it's going to be L over 2. So the longest wavelength that you can have here, that will be the first mode. So it goes up and down. So that means that, no, it's L equals here. So always, if you make a drawing, so then you're sure that you cannot do any mistake, right? So this is half of a cycle. So again, one cycle, and here we're talking about half of it, right? So the length equals half of a cycle. So lambda sub 1 equals 2 times L, and L is 0.64. Okay, so it's 1.28. So the next harmonic, you're gonna have lambda 2 equals L. Okay, because the next one, you're gonna do this. So lambda 2 equals L, which is 0.64 meters. And the next harmonic, so the second harmonic, so the first overtone, that's going to be the wavelength. So it's going to be the speed, which is 150 divided by the speed divided by the wavelength. So, okay, you can use that equation. Or, of course, you can go back to this equation here and V over 2L. But you'll get the same thing. So 150, the speed divided by 0.64. So 150 is the speed divided by 0.64. So that will be 234 hertz. So that will be your second overtone, the second natural frequency. Okay, so that was easy. You can stop the video. Okay, let's see if we have another one here. So number 3, it's a pipe. So open at both ends. So it's a pipe. Okay, so it can be an organ pipe. Will form standing wave if properly excited with antinode near both ends. So here you have an antinode and here you have an antinode. Suppose that we have an open pipe 40 centimeter in length. So this is 40 centimeter in length. Sketch the standing wave. So here you must have an antinode and here you have an antinode. So it means it has here, it can move, right? So if this one is here, and then in between, you need to have one node, right? And then here it's free. So it should do something like this. Okay, so it's like, if you have a wave here, so you're only taking this part here. And that part will be half of the wavelength. Okay, so that will be half of a cycle. So the wavelength here, so the length will be half of a cycle. again. So your first wavelength, which is the longest, will be 2 times 0.4, which is 0.8 meters. Okay. C, what is the frequency? So that means the speed of the wave is 340 meters per second. The speed is the wavelength times the frequency, because this is meters and this is cycles per second. So you get meter per second. So that's going to be 0.8 times the frequency. Okay, so the first harmonics here will be 340 divided by 0.8. Okay, and you get 425 hertz. Second harmonic will be this times 2, the third this times 3, and so forth, and so on. Okay, D, what's going to happen now if you increase the temperature? So the speed of sound is the speed of those air molecules, moving randomly because of the temperature. So that's going to be 350. So you increase the temperature. And what's going to happen to the frequency? It's going to be 350 divided by 0.8. Okay, and you get 437.5 hertz. So the pitch here you're going to hear will be higher. Okay, so it's going to increase the pitch. So if you want to know by how much, so the difference in the frequency, it's going to be about, you subtract, it's about 12 hertz, right? Which is about 3%, 3% increase. If you divide this by that, so the 3% increase. E, next harmonic. So the next harmonics, you still want to have anti-nodes here at both ends, but now you want 2 nodes, right? You want 2 nodes. 1 node, here you had only 1 node, and now you have 2 nodes and 2 anti-nodes. So you want to start from here, and then it's very hard to draw, but start from here. That's your node. Choo, 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 choo. And then go up and there. So 1, 2, 3 anti-nodes and 2 nodes. So you have 2 nodes here. Okay. So now we have, so that's going to be a half, and then you have a half. So that's going to be 1. So it's like if you look here, goes chung, 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 chung. So you have a whole frequency. You have 1 cycle. Okay, so you go from here, go down, and then you go back here, same place. Because you go back to the same place, that's going to be one wavelength. So what you can think about is that when you have a pipe here, you can start by drawing the wave. You can have the wave. Okay, and you have your pipe. So the first one you can fit, you can go from here to there, because that's an anti-node and this is an anti-node. Okay, and then you can go from here to next one will be here, because anti-node. And then the next one will be here and there, and so forth and so on. So that's how you can do it. You can also do the same thing if you have a closed pipe. Let's say if you have a closed pipe here. So you still have your wave. So you have a wave, but at one end it's closed, right? So I have a closed pipe. So the first, and you have an antinode and a node. So node, antinode. So that's going to be the first harmonic. And then node, antinode. So the next one will be this one. Okay, so that will be, they call that the third harmonics, right? So this is 1/4. Then you have 1, 2, 3/4. Node, antinode for close and open pipe. And then here you have your node. The next one will be up to here. So you have 1, 2, 3, 4, 5/4, right? So 5/4 wavelength. Then the next one will be here. You want to have your node, this one, then it goes up to here. So 1, 2, 3, 4, 5, 6, 7, and so forth and so on. So that's one way you can remember those equations without memorizing them. Uh, okay, so I think we did it. Okay, that's it. Slide 33. I think that's it, right? Okay, so the next slide is it's just going over music, and we talked about that again. But when you play an instrument, you're gonna make a sound wave, right? That will propagate in the air until it hits your eardrum, and the waveform, okay, depends on the instrument. So you can use the same instrument, and you can play the same note with different instruments. The pitch will be given by the fundamental, and then the other frequencies that you add up, so the overtones, will give you the quality of the note, right? So the timbre. So for example, here you can play music. So I don't know, maybe it's going to be piano, for example. And you see you have only one frequency here. So you are playing music. That's the complex wave that is produced. But you see that it's one pitch, one frequency that you hear, and you see how it's repeating itself, right? So it's repeating itself. That wavelength here, that wavelength will give you the frequency, the pitch of the instrument that you are playing. Okay, so for example, here you see that you have the cycle here that repeats itself. So the number of cycles per second will be your pitch. Okay, so that will be the frequency that you hear. You don't see the overtones here, okay? But the overtones will let you know which instrument is played. So let's take this example here. I don't know exactly what is that instrument here, but I will give you more examples. So you have if you, for example, if you have an oscilloscope and you put a microphone, you plug a microphone and you play your violin, for example, and you play just one pitch, you're going to see this signal here, that waveform. You see that cycle repeat itself. So let's try to find the frequency. So the wavelength here is 3. So that will be the 3 meters. The speed is 344. So the frequency of that sound, okay, that you are playing with your instrument, it's going to be 344 divided by 3. So that's going to be 115 hertz. Now, if you play a tuning fork, you get a pure tone, right? So you just have one sine wave. And of course, the wavelength here of the number of cycles per second will be the pitch of the tuning fork. And then there is another website if you are interested. So here is the website if you are interested in the physics of music. So it's a very nice website. And I will put the reference in the description. Now, what you can see here, these are different instruments to play music, but they are playing the same note, right? So it will mean the same fundamental, so the same pitch. But if you look at the waveform, they don't look the same. So they're going to have the same frequency. So it means that, for example, for the flute, you see that the cycle here repeats itself. So you can find the wavelength. And if you have the speed of the wave, then you can find the frequency. A violin will have a different speed of the wave. It's going to have a different wavelength, but the frequency, the pitch will be the same. Now, if you use a spectrum analyzer to analyze, to see what are the overtones that hide behind the waveform, you see that the cocktail here that you get for each of them is not the same, but you have the same pitch, the same fundamental. And we discussed that before, but what makes the quality of the tone or the timbre to tell apart a flute from a violin? They are the overtones. You know how much of the second you have, how much of the third you have, or the fourth, and so forth, and so on. A tuning fork has mostly the first mode, right? So that's why you have a nice sine wave here. Of course, you can play with the website here. You can play the middle A. My ear. You can do the violin with the middle A. Oh, you can do the flute with the middle A. So they don't, and of course the tuning fork, very boring. So they don't sound the same here. So what do we have here? So you have piano, and you go from one note to the other one. Okay? As you can compare the waveform and you can look at the frequencies here. So if you want to learn more about music here, I recommend that website. What else about music here? So when you go from here to there, you multiply the frequency by 2. From here to there, you multiply by 2, that will be 1 octave. From here to there, you multiply by 2, it's another octave. So our ear is able to tell the instrument apart because of the tone quality of the timbre, even though the pitches, not the pitches, sorry, because the pitch is the same here. It's a middle A, 440 hertz. So the waveform, of course, is more complex for a violin because it's going to have more and more and more overtones. So it's rich, it makes the tone richer. Okay, that's about music. You can skip that. So interestingly, it's Galileo who developed the Western music scale. So this is for a piano, and you go from one note to the other one to the other one. by multiplying by the square root of the 12 root of 2. So 2 raised to the 112. So go from here to there, you multiply the same number. Okay? So you can learn more about that here. And if you have a piano, for example, if you play 2 notes and if they sound good, okay, so they go well together, it's because the ratio between their frequencies is in the whole number ratio. So between a C here and a G, so Do and Sol sounds good to us. That's because the ratio of their frequencies is equals to 3/2, or it's called also a perfect fifth. This is a fourth. So that for those who are interested in music. So a lot of physics in music. So again, let's look at the website. So this is an interesting website here about music. This is also interesting website. That's going to be acoustic. So a lot of fun simulations that you can find here. See, this is a violin. Again, you see the waveform here. So that will be the change in air pressure. And you see that the cycle repeats itself. And then you have to use a spectrum analyzer. So it's a piece of electronics, right? It looks like an oscilloscope, and you can even do that to even electronics oscilloscope. And you can the machine will do a Fourier analysis, and you can find all the frequencies here hiding behind. So instead of having the amplitude here versus the time, you can have the amplitude versus the frequency. So you can go into the frequency domain, which is interesting because if you are using electronics, you can do all kind of stuff like removing all the overtones, keeping the pitch, the fundamental. So we talked about that last time. Okay, so next class I think I will make a new playlist, and I will try to introduce waves.